calculate the ampacity of motor feeder conductors, it's important to understand the proper procedure, especially when power factor correction capacitors are involved. It's not simply a matter of multiplying the full load amps by 1.25. Section 430.27 directs you to sections 460.8 and 460.9 for sizing conductor ampacity for motor branch circuits. Feeder conductors are sized differently. The approach involves several steps that address the specific characteristics of motor loads and the impact of power factor correction. Here is a breakdown of the steps you should follow. Firstly, determine the motor load. This involves calculating the connected load of the induction motor using the formula motor load in kilovolt amps equals horsepower times 0.746 divided by the power factor. The horsepower, abbreviated as HP, is the nameplate horsepower of the motor, which you can find in the motor's label. The power factor, abbreviated as PF, is also available on the motor nameplate. Secondly, apply demand factors. You must determine the demand factors for the specific application. Table 430.25 provides demand factors for various motor loads. The demand factor accounts for the likelihood that the motor will not always operate at its full rated load. Thirdly, calculate feeder current demand. This is done by multiplying the motor load by the demand factor. This calculation yields the current demand that the feeder needs to supply. Fourthly, apply a correction factor. If power factor correction capacitors are connected in the load side of the motor starter, a correction factor of 0.8 should be applied to the feeder current demand. These capacitors reduce the current drawn from the feeder by improving the power factor seen by the source. This correction is vital for accurately sizing the feeder conductors and ensuring efficient operation. Fifthly, calculate feeder ampacity. Determine the ampacity of the feeder conductors by dividing the corrected feeder current demand by the appropriate correction factor. This correction factor is usually 0.8 for copper conductors rated at 75 degrees Celsius, but this may vary according to the conductor material and temperature rating. The formula for feeder ampacity can be expressed as follows: feeder ampacity equals motor load times demand factor times correction factor divided by conductor correction factor. This formula integrates all the necessary factors to arrive at the correct feeder ampacity. Here is an example to illustrate the calculation. Suppose you have a motor load of 100 kV amps, a demand factor of 1.25 taken from table 430.25 for a single motor load, a correction factor of 0.8 for capacitors, and a conductor correction factor of 0.8 for copper conductors at 75 degrees Celsius. Using the formula, the feeder ampacity is calculated as 100 kV amps times 1.25 times 0.8 divided by 0.8, which equals 125 amps. This means that the feeder conductors should be sized to handle at least 125 amps. It is important to consider a few more points. The National Electrical Code, or NEC, provides guidelines for conductor ampacity based on insulation type and insulation conditions. Select conductors that meet or exceed the calculated ampacity while adhering to NEC guidelines. Also, consider voltage drop. Ensure that the conductors are sized adequately to limit voltage drop to acceptable levels, especially in long runs. Excessive voltage drop can impair the performance of the motor. Coordination and protection. Coordination with overcurrent protection devices is essential to protect the motor and feeder conductors from faults and overloads. Ensure that the circuit breakers or fuses are properly sized and coordinated with the motor starter. When dealing with motor feeders and power factor correction, there are several additional considerations to keep in mind. Firstly, harmonics. Power factor correction capacitors can sometimes introduce harmonic current into the electrical system. It's essential to assess the potential impact of harmonics and implement mitigation measures, such as harmonic filters, if necessary. Secondly, capacitor placement. The location of power factor correction capacitors can affect the overall system performance. Placing them on the load side of the motor starter is a common practice, but other configurations may be more suitable depending on the specific application. Thirdly, NEC compliance. Always adhere to the latest edition of the NEC and any local electrical codes. The NEC provides detailed requirements for motor circuits, including conductor sizing, overcurrent protection, and grounding. Fourthly, documentation. Maintain thorough documentation of all calculations, assumptions, and design decisions related to the motor feeder and power factor correction system. This documentation can be valuable for future reference and troubleshooting. Furthermore, consider using specialized software tools. The electrical design software can simplify the process of calculating motor feeder ampacity and performing other electrical calculations. These tools often include built-in databases of conductor properties and NEC tables, making the design process more efficient and accurate. Regularly inspect and maintain the motor feeder and power factor correction system to ensure reliable operation. This includes checking conductor connections, capacitor health, and overcurrent protection devices. Proper maintenance can prevent costly downtime and extend the lifespan of the equipment. When selecting conductors for motor feeders, consider not only the ampacity requirements but also the environmental conditions in which the conductors will be installed. Factors such as ambient temperature, moisture, and exposure to chemicals can affect the performance and lifespan of the conductors. Choose conductors with appropriate insulation and jacketing materials to withstand these conditions. It's also important to consider the grounding requirements for motor feeders. The NEC specifies requirements for grounding conductors and equipment grounding. Proper grounding is essential for personnel safety and equipment protection. Ensure that the motor feeder is properly grounded in accordance with these requirements. In some cases, it may be necessary to install surge protection devices, also known as SPD, on motor feeders to protect against voltage surges caused by lightning strikes or other electrical disturbances. SPD can help prevent damage to motors and other equipment connected to the feeder. The selection and installation of SPD should be based on a thorough assessment of the surge risk. When designing motor feeders, consider the potential for future expansion. If there is a possibility that the motor load will increase in the future, it's wise to oversize the feeder conductors to accommodate the increased load. This can save time and money in the long run by avoiding the need to replace the conductors later. Also, consider the impact of motor starting on the electrical system. Motor starting can cause voltage dips and other disturbances that can affect the performance of other equipment connected to the system. To mitigate these effects, consider using reduced voltage starters or other techniques to limit the starting current of the motor. In addition to the factors already mentioned, there are some additional considerations when dealing with variable frequency drives or VFD. VFD are commonly used to control the speed of motors, but they can also introduce harmonic currents into the electrical system. When using VFD, it's essential to select appropriate conductors and overcurrent protection devices to handle the harmonic currents. It's also important to consider the shielding requirements for VFD cables to minimize electromagnetic interference. Furthermore, it's important to coordinate the protection of the motor feeder with the protection of the motor itself. The motor starter should provide overload protection to protect the motor from overheating. The feeder overcurrent protection devices should be coordinated with the motor starter to ensure that a fault on the motor feeder will be cleared without tripping the motor starter unnecessarily. When working with motor feeders, it's important to follow safe work practices. This includes de-energizing the circuit before working on it, using appropriate personal protective equipment or PPE, and following lockout-tagout procedures to prevent accidental re-energization of the circuit. Safety should always be the top priority when working with electrical systems. Another important aspect of motor feeder design is the selection of appropriate wiring methods. The NEC specifies different wiring methods for different applications such as conduit, cable tray, and direct burial. The choice of wiring method depends on factors such as the environment, the voltage level, and the mechanical protection requirements. It's important to select a wiring method that is suitable for the specific application and complies with the NEC. When designing motor feeders, it's also important to consider the accessibility of the conductors for maintenance and inspection. The conductors should be installed in a way that allows for easy access for testing, troubleshooting, and repairs. This may involve using pull boxes, junction boxes, or other access points along the feeder run. Furthermore, it's important to label the motor feeder conductors clearly and accurately. This helps to identify the circuit and prevent accidental disconnection or miswiring. The labels should be durable and resistant to environmental conditions. In addition to the technical aspects of motor feeder design, it's also important to consider the economic aspects. The cost of the feeder conductors, overcurrent protection devices, and other components can be a significant factor in the overall cost of the project. It's important to balance the performance requirements with the cost constraints to arrive at an optimal design. When designing motor feeders, it's also important to consider the energy efficiency of the system. Selecting energy-efficient motors, conductors, and other components can help reduce energy consumption and lower operating costs. It's also important to optimize the power factor of the system to minimize losses and improve efficiency. Power factor correction capacitors can be used to improve the power factor, as discussed earlier. Moreover, it's crucial to stay up to date with the latest developments in motor feeder technology and design. The electrical industry is constantly evolving, with new products, standards, and best practices emerging regularly. Staying informed about these developments can help you design more efficient, reliable, and safe motor feeders. Consider attending industry conferences, reading trade publications, and participating in professional development courses to stay current with the latest trends. In addition to all the above points, there are some specific considerations for motor feeders in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust may be present. Motor feeders in these locations must be designed and installed in accordance with the NEC requirements for hazardous locations. This may involve using explosion-proof enclosures, intrinsically safe circuits, and other special measures to prevent ignition of the hazardous materials. Also, remember the importance of proper commissioning and testing of motor feeders. Once the motor feeder is installed, it's important to perform thorough testing to verify that it meets the design requirements and is operating safely. This may involve testing the conductor insulation resistance, verifying the overcurrent protection settings, and measuring the voltage and current levels. Proper commissioning and testing can help identify and correct any problems before they lead to equipment damage or personnel injury. Furthermore, consider the coordination of motor feeders with other electrical systems in the facility. Motor feeders are often part of a larger electrical distribution system that includes lighting, HVAC, and other loads. It's important to coordinate the design of the motor feeders with the design of the other systems to ensure that the overall electrical system is operating efficiently and reliably. This may involve performing load flow studies, short circuit studies, and other types of analysis to assess the performance of the electrical system under various operating conditions. Moreover, it's crucial to have a well-defined maintenance plan for motor feeders. Regular maintenance can help prevent equipment failures, extend the lifespan of the equipment, and improve the overall reliability of the electrical system. The maintenance plan should include periodic inspections, testing, and cleaning of the motor feeders and associated components. It should also include procedures for troubleshooting and repairing any problems that may arise. In addition to these general considerations, there are some specific requirements for motor feeders in healthcare facilities. Healthcare facilities have unique electrical requirements to ensure the safety of patients and staff. Motor feeders in healthcare facilities must be designed and installed in accordance with the NEC requirements for healthcare facilities. This may involve using isolated power systems, ground fault protection, and other special measures to minimize the risk of electrical shock. Also, be aware of the implications of energy storage systems for motor feeders. Energy storage systems, such as batteries and flywheels, are becoming increasingly common in industrial and commercial facilities. These systems can affect the design and operation of motor feeders, particularly in terms of voltage regulation and power quality. It's important to carefully consider the interaction between motor feeders and energy storage systems to ensure that the overall electrical system is operating efficiently and reliably. Another aspect to consider is the impact of electric vehicle charging on motor feeders. With the increasing popularity of electric vehicles, many facilities are installing electric vehicle charging stations. These charging stations can draw significant amounts of power from the electrical system, which can affect the design and operation of motor feeders. It's important to carefully assess the load requirements of electric vehicle charging stations and ensure that the motor feeders are adequately sized to handle the additional load. Furthermore, when designing motor feeders, it's important to consider the cybersecurity aspects. With the increasing use of network devices and control systems in industrial and commercial facilities, cybersecurity is becoming a growing concern. Motor feeders and their associated control systems can be vulnerable to cyber attacks, which could disrupt operations or damage equipment. It's important to implement appropriate cybersecurity measures to protect motor feeders from these threats. This may involve using firewalls, intrusion detection systems, and other security technologies. Remember, the design and installation of motor feeders is a complex process that requires a thorough understanding of electrical engineering principles, the NEC, and other applicable standards. It's important to work with qualified electrical engineers and contractors to ensure that the motor feeders are designed and installed correctly. This can help prevent equipment failures, improve the reliability of the electrical system, and ensure the safety of personnel.